In previous videos, we've explored today's metal 3D printing capabilities and the industry's challenge in developing a full range of functional materials. In this video, we'll examine how the capabilities of additive manufacturing extend beyond design and may change the way we think about designing, making, and marketing products in a broad range of industries, including consumer goods, aerospace, and automotive. Conventionally, we tend to think of a cost-effective design as one that uses basic shapes, often fabricated from basic stock shapes such as sheet and tube. Now, in subtractively manufactured parts, which are most of the world's production, design features are a compromise by necessity. For example, in a thermoplastic part, the designer may want right angles, but the draft necessary for clean mold release often makes this impossible. In a piece of HVAC ducting, a complex organic shape may optimize airflow, but a round section is cheaper to produce. A proper mating hinge will last longer, but a living hinge eliminates an assembly step. There are many examples.
One of the fundamental differentiators between additive and formative and subtractive essentially is that there's almost no correlation between cost and complexity. So as a designer, when you sit down to solve a problem, to design a part, you throw the traditional design for manufacture rulebook out the door essentially.
These design compromises sometimes reduce functionality or quality of a product, but conforming your design to the strengths of the manufacturing process is necessary to meet cost, throughput, and time to market targets. But what if we didn't need to make those compromises?
So you're looking right now at Nera. This is the first fully 3D printed e-motorcycle. We are talking about a functional prototype. So everything is 3D printed here, beside the electronic parts. So of course, like batteries, motor, and HMI is not printed, but all the rest, including the tires, are 3D printed. So we're talking about the first of its kind, right? We have, as you can see, like different approaches here. We had to redesign how standard motorcycle works because, again, we didn't want to use any metal structure. It's fully plastic and 3D printed. So we had some issue to solve, right? You had to come up with some ideas. The first, okay, like the tires is obviously one. Like how do you print tires? So we went with airless tires, right? And you can see that there are two different patterns on the airless tires. One is more hexagonal on that side. On this side, there are more arches. Because of like the shock absorbing system, right? The front tires needs to absorb more shocking, while the back tires, since there is the motor inside, needs to be more hardly and structurized. Another issue to solve was the suspension. We didn't have any suspension. How do we do suspension? And that's why we came out with the idea of having a bumper that you can see is in the middle. So basically the part is like, there is a top part and a bottom part, and the two of them are connected with a TPU 3D printed bumper, which allows you basically, whenever you hit something, the bike squeeze and you don't feel any hits on your back, right? The whole thing is printed in 15 parts. So we have 15 parts. The bigger part is the body, as you can see, is printed in one part. And that's, of course, thanks to our machine, our Big Rep 1, which is a 1 cubic meter 3D printers.
Is it possible? How soon do you think this kind of technology we could see on the street? 10 years, 20 years, sooner?
Of course, it's hard to figure out this. I strongly believe in this technology. I think 3D printing is the future, is the present and the future. We need more application. We need people to focus on application and not just on technologies, like what we can make with these 3D printers, like under an innovation point of view. But again, with the new materials developing, etc., I think this can happen pretty soon.
If there's one thing the 3D printer community loves, it's geometries impossible to manufacture any other way. Now, this freedom of complexity is practical applications. Multiple parts of an assembly can be consolidated into just one part, for example. Or a part can be pared down to nothing but an organic-looking web of structural shapes aligned with the forces bearing on it by generative design. Now, it's important to note that 3D printing isn't totally without constraints. Each 3D printing process comes with its own unique set of design guidelines. For example, an FDM part typically has anisotropic bonding between layers, resulting in lower tensile strength in the vertical axis. Of course, this varies by material and by process parameters. Another basic example is that you can't design a fully enclosed void in a part printed with a powder process, such as selective laser sintering, unless you want your finished part to be packed full of unfused powder. Now, fortunately, the ability to iterate multiple prototypes quickly with additive manufacturing means you don't necessarily need to know all the limitations of your design before you make it. You can iterate your way to the best design at a low cost. In addition, with an industrial printer, prototypes can be made of the same material and build quality as a production part, and the applications are broadening. Nano Dimension, for example, makes a machine which can 3D print circuit boards, dramatically slashing the cost of producing PCB prototypes and even production PCBs at low volumes.
We're doing it at the prototype stage, so you get the opportunity to test your designs many more times before you go to production. So Nano Dimension comes in. Overnight, we print that board. You populate it, you test it, By the way, when you see where you need to make your design changes, take the components off, throw that board in the barrel, and print another one.
Now, one opportunity stemming from the digital nature of additive manufacturing is that designers with little to no manufacturing expertise can now print functional parts of the low-cost machine or order printed parts from a service bureau like Protolabs or Xometry.
It gives you access to infinite capacity and also a much wider range of capabilities. So at Xometry, we not only do 3D printing, we have 6 3D printing processes, and the network model also allows us to add more very quickly and nimbly. Over the past year, we've added stereolithography, which is an older process, but one we weren't doing. And we also recently added HP Multi-Jet Fusion, which is a much newer technology, but something that our customers wanted. Manufacturing as a service allows you to spend your time on the idea and getting it out there versus, building internal expertise in many types of 3D printing or injection molding.
We've started to adjust our process to help customers get to that spot before they have to get into tens of thousands of parts. And even we're seeing advances in 3D printing where doing large quantities of parts becomes cost effective using some of the new technologies like dual laser machines for metals, or using the HP Multi-Jet where you can, doesn't matter the density of the layer, you have a constant build speed. So things like that are making it much more cost effective to stay in this rapid manufacturing model at higher quantities.
Now, this can be a real advantage for startups prototyping or sourcing obsolete replacement parts. Now, add reverse engineering to this mix and we're completing the circle. Physical shapes can be converted to digital files, and digital files can be printed physically at the touch of a button. So how will additive manufacturing change the manufacturing industry? Well, one potentially disruptive idea is digital inventory. Instead of warehousing thousands of spare parts for machines and products, manufacturers can store digital twins of inventory parts and print them on demand. Now, some companies, notably HP, have presented ideas about distributed digital manufacturing, in which a global network of printers can produce parts in local markets, eliminating the need for international shipping.
If you have the files created for the parts that are replaced more often, then you can store them in a virtual warehouse, if you will, and that's just where the G-code resides. So when you need to replace that part, then you just distribute it down to the printer and manufacture it on demand.
And 3D printing may create an era of mass customization. It makes good sense technically. If complexity costs nothing, you can feasibly print 1,000 customized unique parts in the same time as 1,000 identical parts. But is mass customization really what the market desires? I think it depends on the application. Take Smile Direct Club, for example. Now, this company provides a service in which users mail in a polymer impression of their teeth, which Smile Direct Club uses to create sets of corrective dental trays. The company uses HP Multi-Jet Fusion to create these custom dental molds. On the other hand, the car company Mini has launched Mini Yours Customized, which allows users to order individualized door trim and interior fascia. The concept of customization is not new. Take monogramming, for example. But when was the last time you ordered a customized product rather than choosing the convenience of buying off the rack? It's unclear that consumer markets will choose customized consumer goods that don't deliver on a specific need, like the individualized dental molds. Now, will the customized washing machine, for example, have the same impact? We'll see.
We have to think about parts designed to be additively manufactured. Too often, people who are making their assessment of additive manufacturing come to us with a traditionally manufactured part. It's either cast, or it's injection molded, or it is traditionally machined, milling, turning, grinding, all of those things. And that's not really the right approach. You have to start with a functional objective, a functional imperative in mind. But if all you try to do is replicate what you're doing today, and with additive manufacturing, creating something that looks the same and does the same, then it's probably not going to be a great fit.
Additive manufacturing does have weaknesses, of course. One is that the processes themselves, they can be agonizingly slow, taking a dozen hours or more to complete a small build. Now, compared to conventional manufacturing, it might seem like this would disqualify AM from mass production applications. But if the design freedom and other advantages of the technology create opportunities for higher quality and lower cost elsewhere in the product lifecycle, additive manufacturing machines just might become a vital piece of equipment on your factory floor. In the end, your customers will decide, or your competitors will.